Hello guys and welcome. So today we're going to be looking at a Riemann sum example. Riemann sums. Okay. So although this question looks quite complicated, I assure you it's not. Like, all right. I've been putting this question off for a very long time now, so let's get into it. Now, let's read the question line by line. They're saying consider a function y equals x cubed and n equals subintervals with the domain 0 to n. So they're saying from here, let me take my highlighter out. We know that it starts at 0 and ends at a. That's quite important. What else do we know? We know that it's given that sigma n as r approaches n, r is equal to 1 approaches n, right? R squared is equal to this. So we're like, alrighty, cool. And we get to see that the function is x squared. So it's a, what do you call it? It's a square. So you know what we can do with that information, right? We can, first let me bend my paper. Okay. So with this information given, we can actually go ahead and, well, draw ourselves a parabola. If you're confused as to why to perform this step, just trust me on this. Let's just draw the parabola on the positive first quadrant. Alrighty, that's looking good. Okay, this is just to show that the parabola it's a parabola, but we've drawn it in the first quadrant. Now what we want to do is we want to calculate the area under the curve. Let's say this point here, right? The furthest we can go. And let's draw dotted lines, and let's let that be A. Okay, and draw dotted lines here too. Okay, and if this is, what do you call, fy is equal to x squared, if you sub in the point x coordinate A, the y value is going to be, exactly, it's going to be a squared. So you can plot that into. And we can, draw some more lines here. And because they want us, the question is show that the area, total area is equal to this in the upper rectangles. See how it says the lower rectangles there? If they're saying the upper rectangles, we want to start from the top of the line and go to the left. Ready? So let's start from the bottom. We're going to start from here and go down. Start from here. You want to go horizontally until your next line. Go down. Start here, horizontally, and then go down. So here, horizontally, and then go down. So this is what we mean by upper rectangles. Okay, we know this is A. Let's just indicate them that the spacing is A on N. Because if we have actually A, if we're going A spaces, then each interval has to be A on N. And then let this, the start, right? Let this be A on N too, because that's the start. And this is going to be 2A on N. And this point, right? That's going to be A N minus 1 on N. Alrighty? So now if we've labeled all our information, we don't need to go and label all of them again on the x-axis. That is totally not necessary. So, yeah. Let me just zoom in so that you guys can see better. Now what we need to do, let's just label one more fact, that this is actually, if you sub in this value into your equation, then this point, when your x is a n minus 1 on n, is going to be a n minus 1 on n whole squared. Okay, all good. So this is a parabola, and this is the triangles waveform. Now what I want you to do is something kind of unintuitive, but let's go ahead and do it. we want to find the integral of this, and they're asking for the area. So to find the area, you know that we're supposed to, let's write, let me just write area here. Area, it's wrong spelling, it doesn't matter though. Area is equal to the area of each of these boxes. If you see this as a on n, and the top, the height it is going, right, it's a on n whole squared. So let's just multiply it, because we want to sum up all these rectangles to get the area under the graph. So area is equal to a on n, which is the bottom, which is the horizontal, and the vertical is a on n whole squared, because that's what we get, and we sub it into the function they've allocated to us. So a on n and a on n whole squared plus, again, the a on n is going to be constant because that's our interval, but then it's going to be 2a on n now, because the next point is going to be 2a on n, and the one after that it's going to be 3a on n. And this will continue dot dot dot. This will continue all the way up until a on n into a n minus 1 on n plus a on n on a on n. We can just write this as a, but then to make it easier for us to visualize it later, it's going to be helpful when we write it as a and n on n. Okay, yeah, all good. Does this make sense? If it didn't, let me know in the comments. But if you understood this, you basically understood everything there is to know in this lesson. Because after this line, all we're going to do is we're going to do some basic algebraic manipulation. We're going to pull out the a cubed and n cubed, and let me tell you why after doing this. Easy. Now, I do owe you guys some explanation as of to why, what just happened here. Well, basically all I did was, see how when you multiply this term, right, it becomes a cubed on n cubed. All we're doing is taking out that a cubed on n cubed, because it's constant within all the terms. Multiply this one, 3a cubed over n cubed. So when we take out a cubed n cubed from 3a cubed n cubed, we're going to just end up with 3 squared. And getting it in this form is very important, very useful, because now we can apply the information that they've given us here, right here, to go on and substitute this as the sigma notation, the sum of. Alrighty, that's why they're giving it to us. So it becomes a cubed on n cubed sigma n r equals 1 r squared. Ready? Now you're almost done, because they've given us that this, they've given us a value for this too. So let's go and sub that in. And if you have noticed it, this is the value that they've given us, right? So when you write here 1 on 6 n plus 1 and 2n plus 1, right? You do notice that this 6 can come down here, and this n cubed gets cancelled with this n very easily. Easy to spot. So then that becomes a cubed on 6 n squared, right here. This n plus 1 stays here, yes. 2n plus 1. And then now as this n squared, they want one thing in the form this way, right? So we're just going to distribute this n squared into both these brackets. And surprisingly enough, you get what you want. A cubed on 6 is equal to, no, a cubed on 6 1 plus 1 on n, 2 plus 1 on n. And that's it. You're done. That's your proof. That is basically how we do that for the upper triangles. Now, if you want to do that for the lower triangles, you just follow the same systematic process again, and you'll get it. Thank you.